Welcome to Small Talk, where Dan and I invite Rice professors to share their unique perspectives on nanotechnology. Today we have Doug Natelson, professor of physics, who's an expert in nanoelectronics.
So Doug, the first question I have for you is about Moore's Law.
Okay.
In class this week, we talked about Moore's Law and how it has been predicting the growth of the size of integrated circuits and the growth in the number of transistors per square centimeter on a chip. And it's been predicting this for many, many years and been very successful. For almost all of that time, people have been predicting the end of Moore's Law, and so far they've all been wrong. So the question is, what comes next?
So it's important to remember that Moore's Law has been so successful in part because the entire semiconductor industry has decided that one of their key objectives is to follow Moore's Law. So it's not an accident that, or happenstance that they've been hitting those kinds of targets. I suspect, based on, well, there are really sort of different Moore's laws. There's the Moore's Law that has to do with feature size. And lateral feature size, we really are going to run into a fundamental limit in approximately 10 or 15 years. And that really is dictated by the number of atoms that you have to work with. So it's sometime in about 15 years, Intel, for example, is going to be making devices, they hope, that are at what they call the 5 nanometer node, which is something like 30 atoms across, and that is pretty darn close to what they think they can do in terms of the ultimate limits of scalable manufacturing.
And that'll correspond to the smallest feature size in a transistor.
That's
right?
about right, yes. You can cheat a little bit, but that's basically it. And it's also related to the smallest feature size in memory devices that they make.
Right.
And in terms of what's coming next, I think it's highly, highly likely that it will be silicon all the way down to the 5 nanometer node, at least for performance logic and for memory, the sort of things you use in your computer. There are other materials, of course, that people are looking at where you can get higher performance. People are already putting a little bit of germanium into their silicon. That ends up improving their performance in certain ways. I think the real next step, if you want to keep improving the Moore's Law for performance, even though you can't keep shrinking the features, is probably some form of 3D integration.
So what do you mean by that? You would have fatter computers, or
well,
how would that?
Of course, most of the volume of your computer has nothing to do with the chip, right?
Sure.
But yes, instead of right now, computer chips are planar things made with about 40 or more steps of planar fabrication, where it's all on the surface of a silicon chip, and you have a layer of transistors, maybe 2, and you've got wires connecting these things together. And there clearly is a trend toward being able to stack these things. So even when they're stacked, they're still not going to be very thick. But the point is that if you could have 10 layers instead of 2 layers, you could have 5 times as many components in the same footprint. Now, the main challenge there is that if you're not careful, there's no way to avoid heating as a severe problem. I mean, already the processors that are used for laptop machines dissipate a few watts.
I know. I mean, the iPads get hot, right? And that's
iPads get warm, and they're among the most power-efficient things you're going to find. The processor in your desktop computer dissipates something like 20 times as much power as the processor in your iPad, which is why your iPad can't do everything your desktop computer can do. But the point is that even to get there, they've had to do some very clever things about scaling in terms of dropping the voltages that they're using and changing the device size in certain ways so that they still work even at the lower voltages. And it's pretty clear that they're going to run into power density issues. If you just stuck 5 chips on top of each other, you'd have 5 times as much heat, and it would be hard to get the stuff out from the bottom.
Could it ever get so hot that it would melt the actual device?
Yeah, it could.
Really?
Because, well, I mean, right now, if you naively don't do anything in terms of altering the device design or the operating voltages, and you just try and cram in as many devices as the 5 nanometer node will require, you'll have the power density that corresponds to something like a rocket engine or the photosphere of the sun. And so what this tells you is that that's not what's going to happen. People are going to make design changes. They're going to change the way that they scale the voltages. And they're also going to try and alter the way heat gets dissipated and how heat gets carried away from these.
So in consumer electronics, we've noticed this trend already because I remember the first laptop I had, I could actually use it on my laptop. And the current versions, it's too hot to put on my laptop, right? So then this leads to maybe a more fundamental question about the process by which heat is generated at the nanoscale. We've talked about in the class about shrinking wires down. And the question is, does that in any way affect the fundamental physics processes by which heat is generated?
Let me ask, I mean, I think you asked the question, but let me try it another way, because, you know, when you move current through a wire, you generate heat. And my question is, do you generate more heat on the nanoscale, or do you just get more wires in the smaller space? You see what I mean?
So in macroscopic systems, if I take a macroscopic wire, you know it's good to talk a little bit about what the heating process is. So if I have a macroscopic wire and I hook it up to a battery, I'm taking the voltage that the battery produces, right? That gives me the electronic charge times the voltage. That's how much energy I'm electrically dumping into each electron. And somehow at the end of the day, the wire gets warm, so that energy that starts out in the electron ends up in the vibrations of all the little constituent atoms and molecules in the wire. And it's a very interesting question. What happens if I shrink the system down to the point where I just don't have very many atoms and molecules to play with? How does the heat actually get, how does the energy actually get from the macroscopic motion of the electrons into the microscopic jiggling of the constituents? Now, there is an inherent length scale over which these things happen. So the way to think about this at the nanoscale is, here's my electron. It's got a certain amount of energy. Depending on how much energy it has a certain probability of, per unit time or per unit distance, of dumping some of that energy into vibrations. And these vibrations can be really long wavelength things. They can be short wavelength things. But it's got some likelihood of doing this. And what you find is, if you make devices that are long compared to that length scale, then the vibrations heat up very efficiently. If you make devices that are short compared to that length scale, what happens is that the electrons just move through the system and don't actually dissipate their energy in the device itself. So
where do they dump it? I mean, don't they have to put it somewhere?
They have to put it somewhere, because the current times the voltage still has to equal the power that you're dissipating. Right. So let me describe a situation for you. Suppose I've got a metal needle and I've got a metal surface, and I'm going to bring these things into contact at the single atom level. This is something you can do in the lab. It's actually something you could set up as an undergraduate lab experiment if you had a little bit of money. So I can have a gold wire touching a gold film at the single atom level.
You're talking about a gold wire that tapers down in size.
The gold wire
to
tapers
one
down
atom.
in size to one atom. Well, again, at the point of contact, right at that instant, it's always touching at the one atom level first, right? So at that moment, you can actually put 30 microamps of current through that single atom.
And that's how many electrons?
30 microamps is something like a trillion electrons a second.
A trillion electrons a second is about what I calculated.
Something like that.
Yeah.
And
are going through that one little
are going
atom.
through that one little atom. And the atom does not melt. The atom does not get kicked out of the way. Why? Because the atom is very small, and the distance over which the electrons have to travel before they're likely to dump their energy is more like 10 nanometers or something like
Which
that.
is 100
so
atoms or
so the
something.
heat does get dissipated, but it gets dissipated hundreds of atoms away from this little
So
constriction.
if you imagined this to be some huge millions of atoms going down to one atom, it would actually be room temperature at the single atom, but the temperature you would start to measure would increase when there's enough atoms to...
I think a better way to think about it is that it's very hard to define what you even mean by temperature when you're down at the one atom level. But the energy that you think of as being dissipated is not being dissipated locally. It's being dissipated far away in essentially the contacts. So if I have a really short transistor even, what you'll find is that the power starts becoming dissipated not in the channel of the transistor, but it gets dissipated in the source and drain, the electrodes that you're using to push current in and out.
Right. So, and then if we talk about other kinds of conducting systems, wires made of, for example, carbon, we talked in the class about carbon nanotubes, which are these sort of molecularly perfect structures, at least ideally, right? In the idealization, they're these molecularly perfect structures where every atom is on a perfect array and they have some length, right? In that case, would you describe conduction in the same way, or what's different?
Well, if I have a long thing like a carbon nanotube where I still have thousands and thousands of atoms, then I would describe it in sort of similar language. I would say that when I've got this very perfect arrangement of atoms, I can always talk about what the electronic states are that are allowed there. It turns out for metallic carbon nanotubes, for example, you can have states that propagate one direction, you can have states that propagate the other, but you can't have states that propagate off in any goofy angles. They're just not allowed quantum mechanically by the geometry. So that already improves matters in the sense that the rate at which you get scattering, the rate at which you get this dumping of energy, depends a bit on whether you've broken up the perfection. So if the only directions electrons can go are to the right or to the left, then what you find is that it takes a lot of oomph to actually make them completely flip direction and come back the other way. And so that's not very favored.
So they don't run into each other.
They don't run into each other very much in that sense. And the other point is that, yeah, you would find if the length scale over which these things are ballistic, which is the expression we use when something can propagate a long way without scattering, the length scale over which nanotubes are ballistic can be long. And by long, I mean micron length scales.
Wow.
Even at room temperature, if you have things that are very clean and are set up just right.
So just as you said, you can't really understand temperature as a phenomenon on the nanoscale. I have a hard time thinking about what does it mean to have current in an object like a carbon nanotube, which I'm a chemist. I think of that as a molecular system. So I don't think of, hordes of electrons moving down a conductive pipe. It's actually a molecule. So how do you conceptualize what's going on when you have ballistic conduction in a nanotube?
Okay, so this is a very good question. And you can always define current if you imagine drawing some plane through your device and counting how many electrons cross the plane, right? So or you can have a capacitor and you can talk about charging up the capacitor and how long does it take. So defining current in sort of the mathematical sense is not that hard. It is a little bit tricky to think about the process where electrons are going through this thing. Now, if you have a big block of silicon, somehow it seems more intuitive to actually picture electrons bopping along and propagating through this thing, but you're used to, as you say, in a nanotube, you're used to thinking of it as a single molecule.
Molecular orbitals, yeah.
Right. So there is a continuum.
And it becomes even more relevant question when you're talking about molecules that even a physicist would call molecules. In
Like
other words, things that are
C60
small,
or-
like C60 or pentane or something.
Right. So in the case of carbon nanotubes, there is really a continuum that goes from thinking about bulk solids to thinking about things on the molecular scale. And the trick is, when do you pass from one regime to another? So one way you could think about it is, I've got molecular orbitals, and you could...
They're basically fixed energy levels that the electrons can occupy, right?
Right. And so you could think of the situation as, I am transiently occupying the lowest unoccupied molecular orbital, and then I am depopulating it at the other end of the system.
So you're basically hopping over some molecular orbital.
Well, I think you got to be careful. I mean, if you think of the orbitals as delocalized things, then it doesn't make a lot of sense to talk about hopping from atom to atom within the orbital.
Well, it's not an atom to atom, but like, for example, you said the scattering length is a micron, let's say, theoretically in a metallic nanotube. Does that mean that the electron is fully delocalized over a micron in that system?
It's an interesting question on how you really think about the quantum states when we're talking about very, very almost macroscopic length scales. In the case of something like silicon, I think formally at absolute zero, you can think about this electronic states as silicon. Giant molecular orbitals that extend a centimeter, but we don't really think of it that way. What we do is we think about the idea that the electron goes into these states and it actually scatters between these states and spends some time in each of these states and eventually comes out the other side.
And without necessarily losing energy, when you say scatter, that can be an elastic process.
It can be an elastic process and not actually
there's not a dissipation necessarily.
Not necessarily, that's right. Now, when we talk about really small molecules, so we're going to put a benzene molecule between two electrodes or a C60 molecule between two electrodes, I mean, the real difference in terms of regime there and in the nanotube case is, if I have a macroscopic solid, by particle in a box sorts of arguments, the levels are very, very close together. If I have a nanotube, the levels are a bit farther apart because I've got fewer atoms and my box is smaller.
Delta E, which is
delta
the
E, the
species,
level separation
is
getting bigger and bigger. And if I have something like benzene, the
level
spacing is really big. And you know it's big for molecules because that's why these things have colors very often, right? They're big because the energy spacing is comparable to the wavelength to the energy of visible light.
Right.
So you do have to think a little bit more carefully about whether your transport is dominated by only one orbital. In the case of a metal, if I have a copper wire, there's a zillion electronic states that are all very, very close in energy. And so you can kind of seamlessly get kicked from one to the other without really losing much in the way of energy, and that's one regime. Whereas if I have something like a benzene molecule, then I really do have to think about there's a highest occupied orbital, and then way up here there's a lowest unoccupied
Yeah, it's like
orbital.
stairs that you've got really big
And then,
steps you have to take.
Exactly. When you really only have a couple of states, now you have to start writing down explicit quantum mechanics where you think about, well, there's a transition rate for going onto the unoccupied orbital and off again. There's a transition rate for leaving the occupied orbital and filling it back in from the other side. And then you have to think about, if you're really doing quantum mechanics, you have to think about higher order processes and really thinking about all the ways this can happen.
And so you just mentioned sort of two regimes, one of which is sort of this macroscopic regime and one of which is the really rigorously a quantum regime. Would it be fair to say that you would describe a nanotube as something intermediate?
Usually, yes. I mean, at room temperature, I would say so.
I have a question because we're going to be talking in this week about conductivity of simple metals.
Okay.
So I kind of want to go back to the solid state physics view. And my question is, as you have a wire and it's carrying current, and you make that diameter of that wire smaller and smaller and smaller and smaller into the nanoscale, are you going to get a better conductor? Leaving aside heat dissipation, is it going to become a better conductor? And if so, why?
That's a very good question. So the reason you get finite resistivity as opposed to zero resistivity in a macroscopic wire is that the electrons actually don't scatter off the copper atoms, say. They scatter off the defects in the crystal. So the real quantum states in a perfect crystal really are fully delocalized.
And the problem is you can't make a perfect crystal.
Right. But there is some characteristic grain size for your metal. So if you were able to make perfect interfaces and you could get rid of the grain boundaries, so you made your system small compared to the grain size, which again is typically 10, 20 nanometers or something like that, then in that sense the conductivity of the material goes up and sort of maxes out.
So that's a really interesting one idea, right? Which is that there's a natural probability of having a defect in any solid. And if you make the solid smaller, then the probability you're going to have a defect, because you have fewer atoms, is not as high.
Now,
that's one idea, right?
The tricky bit here is that, okay, so now you've made the conductivity perhaps as good as it can be, but the actual conductance, how much current you can really get for a certain voltage, really depends on your geometry. So if you actually make the wire small, it simply cannot support that much current at a given voltage.
So you get less current, but you don't get as much resistivity.
Right. So
but then, of course, you can pack more of them in a space.
But if you put a bunch of small wires...
Right. This could be good. Now, in practice, one of the things you do have to worry about at room temperature is you really do have vibrations of all kinds going on. And so even if you have the wire and it was geometrically perfect, there's some amount of vibrations that will effectively, from the standpoint of an electron, if you think about it, what does a vibration do? Well, it distorts the lattice. And so that kind of acts like a defect. And so unless you're going to freeze out those vibrations, you really still are going to get some amount of resistance.
Yeah,
at 4 degrees Kelvin, in principle, you can freeze out all the vibrations and you can really max out the conductivity. But for a device that's operating at room temperature, you're always going to have some limit which is imposed by the interaction between the electrons and the vibrational modes of the solid.
So I want to switch gears because one of the ideas we talked about last week was the history of nanotechnology and the fortunate or unfortunate role that hype and sort of public communication plays in this discipline, and perhaps a lot of scientific discipline now. So my question really is, what's your perspective on hype? Should we never do it? Do we have to do it in order to communicate with the public? And do you think nanotechnology is different than other areas of science and engineering you've worked in?
So I think you have to draw a line between hype and genuinely legitimate self-promotion or promotion of ideas. So there's nothing wrong, in my view, with saying, if you really believe it, look what this technology could do. That's fine. I think I use the word hype personally in more of a pejorative sense. I mean, hype is sort of, in my view, is kind of unjustified claims.
So in your mind, there's a continuing of hype, and there's promotion, which is okay, but it can descend into hype.
Yes.
Okay. And where's
that's
the
accurate.
bright line?
Well, that's why this is an ethically tricky thing, right? I don't think there's always a bright line. I mean, certainly if someone is saying stuff that they truly don't believe...
So where's your line? I mean,
where's my
what
line?
has to be true for you to talk about the future of your research? the fact that you may be creating new kinds of sensors?
I mean, it's kind of an internal gut check. I think I have to truly believe what I'm saying. I would never say that my research is going to lead to molecule-sized robots swimming through your capillaries, cleaning out your blood vessels, because I just don't think that's true. In the same way, I would have a very hard time saying I do not think we are going to have molecular electronics in the sense of the active region of every transistor in your future machine is going to be a single molecule that has some special function. I don't think that's likely to happen at all. I think the angle where that is a little less crazy is the fact that once you get silicon down to 5 nanometers, then
it kind of is molecular.
It's kind of molecular, which is what I'm always careful to say when describing my own research on these length scales. I say, look, I'm studying heat dissipation in individual C60 molecules as I beat on them in various ways. I do not think we're going to be using C60 as the guts of our future computers. However, C60 is a nice system for other practical reasons for what we're trying to do in the lab, and I think the physics you can get to in C60 is going to be directly relevant to future technologies.
Because those future technologies will involve a small number of atoms.
Correct.
Being active, being the active element.
Exactly. You asked me another thing about hype.
Do you think nanotechnology is any different than other fields when it comes to hype?
I think nanotechnology, in the physical sciences, nanotechnology and string theory are probably the two examples that come to mind of things that, in my view, have been overhyped considerably. Now, I think that the physical sciences run into many fewer problems than, say, the biological sciences or the medical sciences when we talk about hype. I think you can't pick up Newsweek or well, they're out of print now, but you can't pick up a news magazine or the newspaper on any given day without reading about some new thing that is allegedly going to have a chance of curing cancer or solving Alzheimer's disease and so on. And I think the medical community has a tougher problem with hype, in part because it's so tempting to try, when you're trying to make a connection to your audience about why you're doing what you're doing, it's so tempting to say, this is going to solve a real world problem. And the fact is, most drugs don't actually succeed, and most medical research does not, in fact, lead to miracle cures. And all rational scientists are completely aware of this, and Joe Blow on the street is aware of this too if they think about it for a minute. But it's so easy to communicate what you're doing in that area because everyone knows about medicine. At least everyone's got some direct personal experience with medicine.
Yes. Well, so everyone has personal experience with their computers getting hot when they put them on their laps, too.
That's true.
So that's the way that the nano community has perhaps engaged in, as you said, something between promotion and hype.
I think some of the most extensive hype in the nano community has come about in part because of inspiration from things like science fiction, where there really is this vision of either building rocket engines out of single crystal diamond, one atom at a time, or scrubbing out your cancerous cells by having nanorobots scouring through your body looking for disease. Right. And those are great, wonderful ideas, and if you put a gun to my head and asked me, are these absolutely physically impossible, could never happen in 10,000 years, I would be a little hesitant to answer. But certainly in the foreseeable future, neither of those things is coming.
My out on that is I say, I don't know what's going to happen in the 22nd century. So
I'd go farther. I'd say more like the 24th century. But.
Well, so speaking of effective communication with the public, I read your blog, and I'm a fan, and so I wanted to mention it, and also kind of get you to talk for just a minute or two about why you do it and what you hope to accomplish.
Well, I think it's really important for scientists, particularly people who take public funding, to engage with a larger audience than just their scientific peers. And I must admit, I really feel like in physics in particular, the public conception of physics is driven very, very strongly by astrophysics and cosmology on the one hand, and string theory and high energy physics on the other. And in part, that's because on the astro side, you have these amazing, beautiful pictures, and everyone can look up at the night sky and be inspired by the stars. And on the string theory, high energy side, there is this
Origin of life.
origin of the universe
Right.
level of profundity that jumps out at you.
And also $10 billion machines.
Well, there's that too. But I think it really does sort of my discipline a bit of a disservice to have almost all the public attention on physics be directed at just those couple of things. I mean, physics of the solid state variety is directly responsible for many, many things in your life, including, if we're being generous, including things like your microwave oven and your personal computer and the laser in your Blu-ray player and the little accelerometer that tells your iPhone which direction to point the screen and all of these things. And so given how much impact that kind of physics actually has in your everyday life, I kind of wish it had a little bit more popular exposure.
And a blog is a great way to do that.
A blog is one way to do that. I mean, again, a challenge is that some of these topics and some of these concepts really are pretty sophisticated. You need to understand something about statistical physics, the idea that you need to describe large numbers of particles, and you need to understand something about quantum mechanics sometimes. And these are conceptually challenging things for lay people. And so it's really difficult sometimes to convey some of the most exciting things at a level where my mom would understand it.
Thanks so much for joining us, Doug.
My pleasure.
I hope you've enjoyed this episode of Small Talk, where we delved into nanoelectronics, learned about some of the great challenges with respect to how small something can go and still carry current, and also some of the great opportunities that lay ahead. Thanks so much, and see you next time.